All right, good afternoon. Okay, so we're going to pick up what we were talking about last time with descriptive statistics. So last time we were saying, okay, we have some data set, quantitative variable, and we had this process, right? We make a table, we go ahead and plot the table, then we're going to describe it, right? So we gave some different ways of doing that. I want to go into detail now of how we describe these data sets. Make sure this is right. So the one thing what I'm doing right now is actually I'm setting up, just so everyone knows, I'm setting up the video recording. So if you ever do get a little bit behind, feel free to watch the videos. And for some reason this is not taking. Why not? There we go. Okay. So I'm going to go back to the PowerPoint that we were working on last class. It's frustrating. Okay. Sorry. Okay, there we go. And we were talking last time how there were two different centers. We were talking about the center last time of the data set. We said there were two different centers. And we were looking at the mean particularly. Let's bring this up real quick. I changed the notes a little bit, but not much. I changed one or two slides since I posted it last class. Not very substantive changes though. Okay. Okay. So we said, okay, when we're describing a data set, what do we need? We need to know how many modes there are. We need to know the shape. We need to know outliers. And then we need to describe the center and the spread. So we want to try to look at what the center of the distribution actually means. And it doesn't mean what you probably think it does. So we're way back here. I'm going to emphasize again that, you know, when we're looking at the mean, there's a population mean and there's a sample mean. So if we're thinking about this problem in the context, it's not displaying. Okay. There we go. Okay, sorry about that. Okay, so if we're looking at this problem in the context of a real life situation, right, we have our population. We have some variable we're interested in, call it capital X. And we want some number that's going to characterize that variable. So we said the population mean, mu, is the parameter that we're interested in, right? We can almost never get at this because populations are so large. So what do? We take a sample, and we take the sample mean as an estimator of the population mean, okay? So it's good to kind of bear that in mind. Weighted averages we're going to come back to a lot when we talk about expectation values, okay? So we kind of just briefly touched on this. Essentially, you know, a good example is your course grade, right? Each of the different components has a weight. I take the value for that component, multiply it by the weight, and add it up. And when we get to chapter 2 and chapter 3, we're going to use weighted averages a lot, okay? But what I want to do now is I want to talk about this thing called the median. This is the second way that we can kind of characterize the center, okay? The way we do the median, very simple. I'm going to order the data values from smallest to largest, and I'm going to pick whatever data value is in the middle. If I have an odd number, there really is a middle data value, right? If I don't have an odd number, I have two middle values, so what do? Well, mathematically speaking, there's no definition then for the median, but we do what makes sense. We average them, okay? So the value between the average of the two middle values should be our median. We like the median because it's not affected by extreme values. So one of the concepts that we're going to come back to a great deal is this notion of robust estimators. I'm going to write it here. What does it mean to say that something is robust? Have you guys talked about robustness in any of your engineering courses? What does that mean to be robust? Is that a compliment if someone says you're robust, or is that, you know, something negative? What do you think? It's negative? Why? What does it mean?
Well, it depends on what you're talking about. Like, if you're talking about your physical body, then yeah, that's not the best. Robust,
Everybody agree? No?
I was going to say it's a good thing. Typically, it means like a resistance to change. Means something that is strong and sturdy.
I like that idea. What were you going to add?
They use a lot of like terms of food, so I would say it's like robust with flavor, so it can have a positive connotation.
Yeah, so usually in engineering, we think of robust as something that's not easily influenced by other things, okay? So in our context, a robust estimator is going to be some estimator that's not affected by a few, and usually the values we're going to be thinking about are extreme values. So in other words, if I want the sample mean to estimate the population mean, okay, I don't want a few data values to be influencing the value of the sample mean along. Why? Because the population mean is something that's representative of the whole population. That's what I'm trying to estimate, right? So I don't want the thing that I'm using to estimate something that should be really stable and a fixed value. It shouldn't be influenced by just a few values, right? So something that's supposed to represent the whole population shouldn't be easily influenced by a few values. That's the idea behind robustness, okay? So we say that the sample median is very robust. Sample mean is not robust, okay? So some really simple examples. If I have a data set with an odd number of values, I order them, and you can see that the middle value is 2, and that's the median. We use small n for the sample median. And you can see that if you take the arithmetic average, it's 4. So usually the mean and the median, they're not the same. So the question comes down to which one do we use? Again, an even number, you can see that when I order them, I have 2 middle values, 7.7 and 8.9. So what do? The common sense thing, I average them. So the median's 8.3. So here's one of the misuses of the average. It happens a lot more than you think. I'm going to kind of give you a simple hypothetical example. But suppose I run a clothing company in some fictional country, and I have 9 employees, and I pay them all $1 an hour. I pay myself $991 an hour. Nice guy, right? Now, social media picks up on that and says, you know, I run a sweatshop, I'm a terrible person, blah, blah, blah. And I come back and say, no, you guys got it all wrong. Average salary for my employees is $100 an hour. How could you possibly say I have sweatshop wages? Who's right?
Both.
Both of them are right? How's that? Can both of them be right?
Well, the mean salary is $100 since there's 10 employees, $1,000 an hour.
So I'm not lying, that is true, but I also do run a sweatshop. That's kind of obvious, right? So how can this be? How can we have 2 different conclusions from exactly the same data? All right. So here's kind of what's going on. Let's take a look at what's happening. So here's our data. Okay, those are the hourly wages. Sure enough, the mean's $100 an hour. The median you can see very easily is 1, right? The 5th and the 6th values are the same. So the question is, if we're talking about a major essential tendency, something that's supposed to measure the middle of the data set, I have 3 options, right? I could choose the geometric midpoint, okay? I could choose 500. I could choose the arithmetic average, which is 100, or I could use the median, which is 1. The key idea here is that when we're talking about the center of a data set, what we're thinking about is the data, is the value that the other data values are kind of centered around. So which value are more the data values centered around, the median or the sample mean? Clearly the median. In fact, they sit right on top of it. It's not centered, they are, okay? So notice that I was kind of implying, when I said that it was $100 an hour, I was kind of implying that the average was really representative of most of the workers. Most of the workers kind of had their salary around $100, which isn't the case. So you hear this old saying, they say statistics don't lie, but liars use statistics, right? This is a classic example. But this happens more than you might imagine. Very often it happens just through people being naive and not understanding these sorts of situations, because they really do occur in real life. One of the things that happens a lot, hold on, I think I went a little too far. Oh, I just want to kind of illustrate how this happens in engineering, for example. If you think about a skewed distribution, okay, the tail of the distribution acts like an outlier. It acts like an extreme value. So when you look at the median and the mean tends to get pulled out more towards the tail. Okay. So this is the median, the center of the data set. 50% of the values are above and below it. And you can see that they're more centered around the median and the mean. Whereas with a right skewed data set, the same sort of thing. This tail acts like kind of like an outlier in a sense. It's drawing the mean out towards the tail. Okay. So in this case, the median is more representative of the center of the data set than the mean. And of course, when they're symmetric, it doesn't matter. The mean and the median, they're basically the same. So we don't worry about it then, okay? So when we have skewed distributions, and that example with the salary is kind of an extreme case of that, right? That was a really, in fact, it wasn't a skewed, it's because we had an outlier, right? You can see that the mean's very much affected. So the median's robust and the mean's not. Okay, so how do we do this in StatCrunch? So let me show you very quickly. It's actually quite easy to compute summary statistics. I'm going to go back and use the F16 data that we had from last time. And we're going to compute a thing called summary statistics. So a statistic is what? What is the definition of statistic again? You're taking statistics, so you better know what the definition of a statistic is. Go ahead.
Data you get from a sample of population.
It's close. It's something that we're going to compute from that sample, right? So a statistic is anything that we're going to compute, all right? So these summary statistics are going to be statistics that kind of summarize the main parts of this data set. Let me scroll down here if I can. There we go. And so suppose, for example, we want to look at the accidents, okay? So we did this plot before with the histogram, right? I'm going to put the mean and the median on. So the mean's going to be in green. Man, I'm not seeing this thing here. Where is it? And the median's going to be a red line. And we note that sure enough, the distribution is right skewed. The mean's being pulled out a little bit more towards the tail. One thing that you should be aware of, though, is that that comment that the mean tends to go out towards the tail is not a mathematical fact. And there are counterexamples. So a lot of people think whenever you have a right skewed tail, the mean is always greater than the median. And that's not true. I can easily think of counterexamples to that. So it's generally true, but not always, okay? Which means you have to look at the data. You can't just mindlessly assume things, right? Now, how do we actually compute these things? Suppose I want to know what is the actual number. So we go to stats, summary stats, and I want to compute the statistics for the data that's in one column. And I'm going to choose accidents. And I'm just going to compute, the sample size, the mean. I'm going to come back to the standard deviation a little later. Does not want to behave. I'm going to compute a couple other things just for right now. The median, the range, and you could just choose them all. You can just run your cursor and it'll choose them all, but I don't quite want to do all of that, okay? Come on. Okay. And you click on this and you get all these values. And I'm just going to focus on the median and the mean. So you see that the median is 9, the mean is 9.9. It's a little bit above, just like we thought it would be. Okay. So summary statistics are easy to talk to, easy to get in StatCrunch, and we're going to come back to this table. I computed a few extra things here also. So let's think about this for a second. One of the things that we know is that when we look at the lifetime of a component, if we look at the whole population, okay, we look at the distribution of the lifetimes. So this is the lifetime of some component. One of the things that tends to happen is that these lifetimes tend to be strongly right skewed. They tend to have tails that look like that. Okay. And so this is some measure of frequency, okay? I'm not going to put too fine a point on that. And so we have to think about when are we going to report the mean, when are we going to report the median. So suppose, for example, a vendor is trying to sell you a certain component, and they want to tell you the statistics on the lifetime. Which are they more likely to tell you? Are they more likely to give you the mean or the median for the lifetime? What do you think?
Median.
The median? Why the median?
People generally give the mean all the time. It's the default.
They do, but we know that that's not always right. Like in that last example, we saw the median.
A median would be much more useful for a better example.
So who else?
Because with a median, you don't have any of your outliers. Like you don't have anything that's, like for example, your component is going to wear down. You don't have anything that's over towards the right. You just keep everything keep the longest period of life.
So I'll tell you what, so let me do this. I'm gonna play a devil's advocate. Suppose the vendor has an agenda they want you to buy, okay? Which they probably do. So kind of keeping in mind their purpose that they want to try to convince you, which would be more convincing to you if they gave you the mean or the median? The mean, right? So because it's gonna be bigger, okay? So you have to be careful. So in this case, they're probably gonna give you the mean. But if you want to estimate, suppose you're testing a component, and you want to know, is that really unusual, that lifetime I got? What's the value that you're going to use? You're going to use the median, right? Because that's the value that most of the other data values should be centered around. If it's really far from the median, then you know something's wrong, okay? So you have to be aware of these things. They happen a lot. If we have more time, we'd go into some really interesting case studies. Okay, so just to kind of recap, right? Outliers are strong skew, we use the median. If it's symmetric, we use the mean. One of the things you want to be careful about in this course is the difference between process and guidelines. So for example, when we want to describe data, we always go through the same process: table, plot, description. Okay. How we do those steps depends upon the particular data and why we're looking at it. Okay. So how do you deal with the fact that very often you're not going to have a symmetric distribution? It might not be really skewed a little bit. So like in that example that we just had, which would you use? The mean or the median, right? So here are some suggestions, okay? You can compute both measures for the center. That's being honest, that's being fair, that's being very objective, okay? You're not choosing one or the other. Very often, though, what people do is they trim the data set. They'll take off the 10% highest, they'll take off the 10% lowest, and they'll look at the middle 80% and they'll analyze that. They'll take the mean and the median of that, okay? That's usually what people do in practice. What you should do depends on your situation. So one of the things that you kind of want to bear in mind is that statistics is a lot like golf. Not in the sense that it's frustrating, you know, but in the sense that if you think about when you hit a ball near the green in the rough, like 50 yards away, right? You never see anybody go to the ball, take out a device that'll measure the distance of the pin, and then go to a chart. Say, oh, okay, I'm 50 yards away, so I should use a 9-iron. People don't do that, right? They have in mind the different tools they're going to use. They might say 8-iron, 9-iron, wedge, right? They kind of know, but what do? They go and look at the situation. How's the ball line? How deep is the grass? Do you have to get over a shrub or a sand trap? Then you might want to hit a hard wedge, right? Same thing here. These are guidelines, and that's one of the confusions that people have. They think these are rules. They're not. You have to look at what you're trying to do, and then you decide how you're going to treat the data. And very often you'll treat different data sets differently, okay? So here's a really good question. So you made a comment that we always use the mean. And here's kind of the weird sort of thing. If you go back to this and you look at this chart, you realize, well, you know, median is always a safe bet, right? I mean, if it's symmetric, the mean is equal to the median. So why not always choose the median? And why do we make such a big fuss about the mean? Why do we care about it at all if the median is always the right choice? Well, here's kind of one way to think about it. One of the big problems that we're going to be dealing with is we're going to generally have two different populations, and we want to see if they're different. So you have some sort of semiconductor that's doped and not doped, and you want to see how the properties are going to be affected, okay? So you actually want a measure that's going to be sensitive to changes. Guess who fits the bill? The mean. Because the mean's not robust, because it is affected by small changes, it's going to let you detect differences between populations. So when we do descriptive statistics, we're interested in the median, but when we do our analysis, we're going to see even that for skewed distributions, the mean is still what we want to focus on. So there's this difference in how we look at these things. Okay? So any questions on the center? Everyone's pretty good? I know a lot of the stuff that you've seen, but kind of the interpretation you want to think about a little bit. Okay, so now we're going to talk about the last piece of the puzzle, which is the spread. And so one of the things that you're seeing a lot, especially in the aerospace industry, is that the large aerospace companies are beginning to actually make their own parts. So Wall Street Journal 2 weeks ago just ran a piece about Boeing's beginning to increase their own fabrication divisions. So suppose you're the manager of a new Boeing division and they're making seals for doors. So Boeing's now going to start making door seals. And you have these two different methods for making doors, right? And so you go ahead and you're going to test the stress for each of these methods, okay? So for method 1, the first seal that you tried failed at 6 psi. Second one you tried failed at 24, which is really good, right? And so on. With the second method for making the seals, the first one failed at 13 psi. Second one failed at 15 psi. So which of those methods do you think is better? Your boss comes to you and says, okay, you got the data. Which of these should we adopt for our company? What do you think? First or second?
The one with the least amount of spread, probably, right?
The one with the least amount of spread? Okay. So why is the spread important? I mean, I look at this and you know, this one failed at 24 and this one failed at 23. Is that really good?
Are you still asking me?
Yeah.
Okay, yeah, well, it's good, but I mean, it also did 6, so, you know, it's not super reliable.
Exactly. And you want to have consistency. So when you tell somebody, I mean, when you guys, and a lot of you know more about this than I do, I'm sure. But you know, how did the Air Force schedule maintenance? They schedule it based on where they think the lifetime should be, right? So you know, if they think the lifetime should be around 15, and this thing fails at 6, someone's going to have a really big lawsuit on their hands. Not to mention other complications. So you want consistency. That's exactly the point. So I think all of you are kind of aware of the fact that consistency is really important. And I actually jury-rigged this, of course. I kind of set this up, right, so that both of these data sets are symmetric. For really small data sets, you won't get perfect symmetry, but this is pretty symmetric. That's pretty symmetric. So we use the mean. They have the same mean, but just like you said, spread of the one's a lot bigger than the other. So how do we measure the spread? How do we quantify it? What do we use? And I want to make a point here that's really important, though. There's one thing that I want you to start thinking about. I know everyone has this notion in their mind that large spread means it's not consistent. That's good. But the spread is also related to the mean. So here's how we want to start thinking about the spread a little bit, okay? Suppose we have these two different distributions, and now instead of 5 measurements, maybe I have 1,000, okay? So for the one method, I have this really big spread, okay? It's symmetric, it's centered around 15. And for this other method, I thought I had another one. Nope, it's still green. And for the other one, I have a really small spread. Now, here's how we want to think about this. when we have a large spread, I'm just going to use an arrow for high spread, okay? When we have a large spread, the way we interpret the mean is that the mean is just the center of the data set. I'm going to capitalize the word just. It's the center of our distribution. You guys don't mind if I abbreviate distribution, okay? And so this is our general way of thinking about the mean, right? But when the spread is small, when we have low spread, the mean has a different interpretation. The mean is representative of what I expect to see if I draw one individual. For one individual. Why? Because the spread dictates how much wiggle room the values have, right? So these values, they cannot go very far from the mean. So the spread kind of dictates or influences how we interpret the mean. Okay. Here I may not really interpret the mean of what I expect to see in a single draw because there's a lot of spread. Okay. I can very easily get a data value way out here. Here I can't get data values very far away. Yes, sir.
So when you're comparing the green distribution to the red distribution, so the green distribution is the individual, is it the standard deviation? We should consider that.
So we're going to talk about the different measures, but the idea is that, you know, we're going to think of, and this is a really good question, and so I'm going to kind of get a little bit ahead of the game and tell you a little bit of a spoiler. The standard deviation is like a unit of measurement. Just like you measure things in terms of inches and stuff like that, when we're looking at a distribution, we measure distance in terms of standard deviations. And standard deviation, but we haven't talked about it yet, is one measure of the width. And there's a rule. Does anyone know the rule about how many standard deviations you can tend to be away from the mean? Have you guys come across that rule?
Is it like 2?
Yes, it's around 2 or 3 depending on how strict you want to be. So the idea here is this is kind of like a little ruler. The 3 standard deviations are here. For this distribution, okay, this is my measurement. I can't get more than 3 standard deviations away in general. And for this one, the standard deviation is going to be really big. We're going to come back to this notion. So if it doesn't make a lot of sense right now, that's okay. But to answer your question, yeah, that's kind of what's going on here. Okay. So again, you know, in practice, we all know that the importance of the spread is it's a measure of consistency. We always want consistency, okay? In theory, what we're going to see is that, you know, the variability is a measure of how much spread there is around the mean, but it can also be indicative or representative of what I'm going to see in a single draw. So there's kind of a practice and a theory of this. So how do we measure the spread? There's 3 different ways, okay? The worst way is the range. In other words, I'm going to take the smallest and the largest data values, subtract them. So that interval, the length of that interval that contains all the data is going to be considered the range. The range is totally unaffected by the distribution. Notice this is left skewed, this is uniform. They both have the same range of 3, okay? So for that reason, we never use it as a measure of spread because it's sensitive to the most extreme values, right? If there's ever an estimator that's not going to be robust, it's the range. Even though we don't use it as a measure of the spread, we always compute it. I always want to know what range of values something can take on, okay? So we compute it, but we don't use it as a measure of the spread. In fact, it's the worst measure of the spread. And yet you'll see people do that, believe it or not. So we usually use this thing called variance. And the variance is essentially the average of the square distances of the data values from the mean. So notice that there's 2 different variances here. There's a thing called the population variance. In other words, if I want to take all the data values in the population, subtract them from the population mean, and square all those, sum all those square distances and take the average, that's the population variance. So this is a parameter, comes from the population. We would like that, but we generally can't get it. So sometimes you hear us something about the average squared value. That's the average of the squared distance, okay? Of course, we can't get the parameter because we can't get everybody in the population, so we usually settle for the sample variance. So it's written as S squared, and it's almost the average of the squared distances from the sample, except what's different? Why is it not exactly an average? In order to be an average, I'd have to divide by what?
You have to divide by n, but that's n minus 1.
Right. So it's really close. And of course, when n is large, it's almost the same. So we use S to estimate sigma, and we're going to talk about why this n minus 1 is there. Near the beginning of probably April, we'll start to talk about it. How many of you guys have heard about something called degrees of freedom? Okay, so it's kind of like a mystery to most statistics students, but we're going to talk about why this quantity has what we call one degree of freedom, and that's why we have to put that n minus 1. But we'll jump off that bridge when we come to it. But again, the thing I want to emphasize is that when we have estimators, they're always estimating something from the population. This is what I want. It's in the population. I generally can't get it. I can't get everyone in the population. So I'm going to estimate it using the sample. Okay. By the way, one way you can remember parameters, they're almost always Greek letters. Why is that helpful? Well, think about it. You don't know parameters, right? Have you ever heard the old phrase, it's all Greek to me? What does that mean? It means that you don't know it. It looks like a Greek language, right? So all Greek to me means you don't know it, while the parameters are things that you don't know. So that's kind of one way to remember that parameters are always Greek letters. Okay. But we're usually not interested in the variance. The variance is actually not a good measure of the spread, because if you think about it for a second, suppose x was the lifetime, okay? I subtract it from the average lifetime, I square it and take the average, okay? What units does that quantity have? So lifetime is units of time, right? So if I compute the variance for the lifetime, what are going to be the units?
Times squared.
Times squared, which is not a really good measure of the spread. So usually we take the square root. So one way to kind of think about this is we're interested really in what we call the standard deviation. And so whether it's the population or the sample, the standard deviation is always the square root of the variance. Okay. And sometimes we don't want to write this out, so we write SD, or sometimes standard deviation, or some variation thereof. And sometimes for variance, we write var. And we're going to see that we use a little better notation than this, but we kind of abbreviate these things. So again, the population standard deviation, the square root of the population variance, sample standard deviation, square root of that. All right. The thing that I will mention, though, is the variance we're going to use a lot, because it turns out theoretically the variance has a lot of nice properties. We're going to see that a lot of statistics, when we're trying to do the theory, the variance is kind of a natural way. So it's a really important measure, but when we're reporting the spread, we generally use standard deviation. Again, very sensitive to outliers. If you think about what's going on for a second, first of all, it's using the mean, which we know is sensitive to outliers. So think about that skew distribution. See that in your mind? The mean's pulled way off there, way off to the tail, right? Now what are you doing? You're taking the distance from this value way out in the tail to all the other data values, and you're squaring it. So you're actually amplifying that skew, right? So standard deviation, very sensitive to outliers, very sensitive to skew, just like the mean. So how do we think about this? Okay, we have two measures, and neither one of them are robust. The range is not robust. The standard deviation is not robust. So what do? We're going to introduce a new concept. And this concept of percentiles is one of the most important concepts in this class, and it kind of is going to require you to liberate your mind a little bit. One of the things you're very used to doing, and I was the same way when I was a student, is you're used to talking about the probability of certain values happening. Like, for example, if I asked you the question, what is the probability if I randomly choose a student they're going to be 6 foot 6 inches tall. What is that probability? And all of you have in your mind some number, and you're all wrong. Well, let's see. What do you think the answer is? I'll take some guesses. Would you believe 0? No, you don't. Why is it 0? It is 0, but why is it 0?
You have a discrete height, the probability converges to 0.
So let's think about it. Yeah, so what does it mean to be 6 foot 6 inches tall? Well, it means that you're exactly 78 inches, right? It means that you're 78.0000000. Is anyone exactly that? Very unlikely, right? So we have to kind of liberate our mind. We have to give up the notion of talking about, when we're talking about continuous random variables, right? We have to give up this notion that we can talk about the probability a certain value occurs. But what can we talk about? We can talk about percentiles. So I can say, like, Michael Jordan's supposedly 6 foot 6, right? I can say that he's in the upper first percentile or the 99th percentile. That makes sense. So we're going to see that almost everything that we're going to talk about in this class is always going to be cast in terms of percentiles. Okay, this is going to be how we think about things. So this is a nice segue or a nice introduction to this idea. So what we do is we think of the data values kind of like a dot plot now, or on a number line, right? And I'm going to have this thing called the first quartile. I denote it Q sub 1. This is a data value that's the 25th percentile. 25% of data values are less than that. The median is the second quartile, right? By definition, the median is a data value that 50% of the data values are less than. The third quartile, Q3, is the 75th percentile. So we're going to start thinking about data that way. And now, how do we measure the width? Well, what we do is we're going to look at this thing called the interquartile range. In other words, it's going to be the range between the two middle quartiles. It's going to be the value of Q3 minus Q1. This width, the interval that contains the middle 50% of the data, that's going to be the interquartile range. So we're going to use that as a stable measure of the spread. Not sensitive to outliers or skew. You can prove mathematically, you can take about 20% of the distribution and mix it all around wherever you want, and the IQR is very, very stable. Okay? One thing I'm going to mention very, very quickly, this is not in the book, and so you won't be tested on it, but for practicing engineering, it's very, very useful to know. This is called the coefficient of variation. Engineers use this a lot. This is also a measure of spread, but not one that they use in the book. And essentially what we're doing is we're seeing how big the spread is relative to the mean. Okay, so the spread here is the sample standard deviation divided by the sample mean. So we're kind of measuring the spread relative to the mean. You see this in engineering a lot. I don't know if many of you saw this or not, but or if you're familiar with this, but about 1.5 years ago, there was a big, and we may do this data analysis in class actually if there's enough interest. There was a big problem with Flint, Michigan. They kind of changed their water supply, and what happened was the water was really terrible. It just became downright dangerous. And so an engineer from Qunat, civil engineer, went in. I forget his name, Mark. His name escapes me. But he analyzed the water supply, and it turns out that this is what they use a lot in engineering. And so he gave a really nice example. It turns out that spread of the coefficient of variation for harmful minerals in tap water has a huge amount of variation. And so you really have to be careful how you measure heavy metal when you're just doing like tap inspections, okay? And so this is kind of a measure of how much variation there is. When the coefficient of variation, this ratio is greater than 1, it's kind of high, okay? When it's less than 1, it's low. When it's around 1, it's kind of moderate. But just something to know for just because practicing engineers use it a lot. Okay, so which spread do we use? Well, notice that we have the same sort of rule for the spread as we do for the center. When we have outliers or strong skew, we're going to use interquartile range. Okay, when it's relatively symmetric, we use the standard deviation. Okay. Again, in practice, what do? Good rule of thumb is if you're not sure, compute both, or you can use a trim data set. All right. One last rule of thumb I'll just mention very briefly. So sometimes when people are trying to figure out whether to use the mean or the median. They ask this question, you know, how large does the skew have to be to use the median? And while there is really a good answer to this, when we're doing descriptive statistics, we're not doing analysis. We're just describing. So we're not trying to put a fine point on this. But a general rule of thumb is that when the sample mean, the difference between the sample mean and the median is greater than 1 standard deviation, we tend to think that the data set is so skewed, we should use the mean. So when this is true, we tend to use the mean. Tend to use the median. In other words, this is saying that the skew is pretty great. The difference between these two measures, which should be close if it's symmetric, is very large. And in fact, it's larger than 1 standard deviation. Okay. Again, it's a guideline, okay? Not a hard and fast rule, just something to guide your thinking, all right? So the last thing we want to talk about is this thing called a box plot. And the way I think of these sorts of methods are, first, it depends upon sample size. So we know that for small samples, we tend to make dot plots. Why? Because we don't have enough points to fill out a curve, right? You saw that with that dot plot on the F16. There really weren't a lot of data points to kind of make a nice curve, okay? But when we have around 30 or so, we tend to use a histogram. But here's the problem with histograms. And you guys haven't experienced this because you probably haven't worked with them a lot. But they can be very, very sensitive to how you bin the data. I can easily take data sets and bin them slightly different ways and get very different looking histograms. And the reality is that sometimes we don't really want that detailed picture. Histogram is a very detailed picture. Sometimes we just want kind of a gross picture of what's going on, okay? So we're going to go ahead and use a box plot. And here's what a box plot is. So remember, we have this rule, table, plot, description, okay? So with a box plot, we make a table. This is called the 5-number summary. We record the minimum value, the maximum value, and then the 3 quartiles. Notice there's a lot of information in those 5 numbers. It gives me information on the range, the interquartile range, and it also gives me a measure on the median, okay? So it tells me the width of the data set, and it tells me the center, okay? And what we do is we go ahead and we basically plot these values. And so here's how it looks. The quote-unquote box part, okay, so we draw the box first. So the end of the box is at the 1st quartile, okay? The top of the box is the 3rd quartile, and the median's the line in the center. And then we have these whiskers. Sometimes people call this a box and whisker plot, okay? That looks a little bit like a cat, right? There's a whisker out here that goes out to the smallest value, and a whisker that goes to the largest. So let's go ahead and make a box plot of this data for our F16s. So I'm going to say graph, box plot, accidents. I'll go ahead and, well, the median will already be in there, right? And I'm going to change this so that it ends up being draw box horizontally, so that the box plot's horizontal. And I want to compare this box plot with this distribution. And I'll try to do it on the same screen so we can compare them. And I'm also going to try to make the scales the same, okay, so that it's a fair comparison. So just give me a minute here. Okay. So I need to stretch this out a little bit. There. Okay. So you can see that this is the first, and in fact, if I bring up, in fact, I'm going to bring up the 5-number summary I just did a second ago, which I hid somewhere, didn't I? Here we are. Okay, nothing up my sleeves, right? Okay, so you can see that the first quartile, which is at 5, that's where the end of the box is, right? Q1 is at 5. Q3 is at 14, that's the upper end of the box. The median's at 9. The IQR, the width of the middle, 50% of the data is 9. Notice that the shape of the box plot reflects the shape of the histogram. What do I mean by that? How does that histogram kind of reflect what's going on? I mean, how does that box plot kind of reflect what's going on with the histogram?
Share the same underlying data.
It's exactly the same data set, but could I tell that this data set had a right skew to it? How can I tell?
Because the right whisker or whatever is a lot longer than the left whisker, and even the middle box is the right one is larger than the left one.
Right. So there's two indications. Tails are indicated by one whisker being longer than the other. Okay. Takes a little while to see this, but this whisker is longer than this. Notice also that the median tends to be shifted inside the box. Okay. So you can kind of get this from this. But box plots, you have to be a little careful. They're not the be all and end all. What if I had a bimodal distribution? Could I tell that on box plot? No. Okay, so you have to be a little careful. That's why I said these are guidelines, they're not rules. When I plot data myself, I plot it both ways. And then I see which one better or more effectively communicates what's going on with the data. Okay? But it's kind of nice. You can see what's going on by looking at the box plot. Questions about that? Everyone's good on that? Okay. I'm not going to talk a lot more about box plots, but I want you to read the book because there are some little subtleties. How do I detect outliers? What would an outlier look like on a box plot? Well, it turns out that this description that I gave you is a little bit of a simplicity. I mean, it's a little bit of a simplification. Sorry. Let me go back. So notice that I said this was the largest and the smallest. Well, I lied a little bit. So I'm going to leave you with one last piece of information today. When we do box plots, here's what we actually do. We draw Q1 and we draw Q3. And then we draw like an invisible fence. Kind of like with your dog, we have the invisible fence, right? This is called the fence length. This thing goes out 1.5 interquartile ranges on both sides. Okay? 1.5 IQR. This is what this distance is, okay? And what we do is we plot the data value that's farthest out in this fence length, okay? So if I had a data value that went all the way out to here, this is what I actually plot. If a data value lies below the 1.5 fence length, it's shown as an outlier. Either the program will make a star or put a dot out here. It's an isolated spot, just like you think of an outlier as being, right? Same thing here. The program's going to plot the largest value within the fence length, okay? So let's suppose we had a left skew. It would look like this, right? So this would be a distribution that would be left skewed. Let's see, it would look kind of like this, right? And had one outlier. So you have to kind of bear that in mind. It's not just the smallest and largest. It's the smallest and largest within that fence length, okay? And there are reasons why 1.5 times IQR is chosen as the fence length. This is called the fence length. Okay? And I'll let you read over that. It's pretty straightforward there. Okay, that's pretty much all for today. We're at the end of time. If you have any questions or problems with the homework, just let me know. All right, thanks a lot.